Today's video is about enthalpy change, which we're going to have to define. In the past, we've talked about enthalpy and just assumed that it was the same as energy. It's not, so we'll clarify that today, and then talk about how we can model energy change during phase changes and during chemical changes. To get at the idea of the difference between energy storage and transfer, we should talk about something called a state function. State functions are quantities that don't depend on the pathway between 2 points. Here's an analogy that might make it easier to understand this difference. I live in Hayward, Wisconsin. I have a brother that lives west of Chicago, and if I want to go to his place, there are two ways that I could think about getting there. One is I could look at the difference in latitude and longitude that I would experience as I travel from Hayward to his city. GPS coordinates are an example of a state function. I could choose multiple pathways to get there, but all of them would start and end in the same two places. I could choose to just drive there the most direct route, which is 411 miles. I could choose to go to the Twin Cities and visit some friends and then drive there another pathway. That would be 536 miles. Or I could go over to the Appleton area and the Milwaukee area where two of my other siblings live and visit them on the way down, and that would take 665 miles of travel to get to Chicago. So the odometer reading does depend on the pathway that I took to get there, so that is not an example of a state function. Okay, so let's leave the map behind and look at something involving energy. Imagine I have a car battery that's fully charged up, and then I fully discharge that car battery in two ways. One is I just hook up a wire to like a bare wire and just let it get super duper hot until the battery's dead. Or I could hook up the wires from an electric fan and let the fan blow until the battery is dead. In both cases, the total change in energy that I would experience is the same. However much energy was stored in the battery, which would be about 4,500 kilojoules, I lost all of it. But heating and working would not be the same in these two different discharge strategies. In the first one, there would be no work done approximately, but lots of energy would be transferred through heating as that coil got super duper hot. If I used it to run the fan until the battery was dead, there would be very little energy transferred through heating. The fan motor might heat up a little bit, but most of the energy would be transferred through working as I would cause the state of motion of the air molecules that go through the fan to increase. So work and heat are not state functions. Now let's talk about the first law of thermodynamics, which I think we have referenced before, but let's kind of formally define it. The first law of thermodynamics says that the total energy in the universe is unchanging. Now, we're not usually concerned about the whole entire universe. We're usually concerned about a particular system. So for a system, what that means is if there is any change in energy, that has to be because of energy flow through working or through heating. Because inside that system, it cannot destroy or create any energy. In a system where work is not possible, then that means that the total energy change just reduces to Q. This occurs, as I've said, when the change in volume is zero, when volume can't change. And so heating at constant volume, if you measure this in a calorimeter, that would be a bomb calorimeter that we talked about in a previous video, that's equal to delta E. In a system where working is possible, where there is some work energy transfer, then the first law of thermodynamics looks like this, and you have to include the W. Remember, when pressure is constant and volume can change, the quantity of work is pressure times change in volume. And we're making the convention here that working is positive when energy enters the system through working, and it's negative when energy leaves the system through working. So if the gas is expanding, in other words, if delta V is a positive number, then that means the system is losing energy because it's causing the expansion. So that would be a loss, so we put a negative out there. If the gas is being compressed, then delta V would be negative, and that's actually an increase of energy for the system because the outside surroundings are adding energy to the system. So that negative sign has to be in there because of those conventions. So now let's get at what enthalpy is. The energy that we measure in a calorimeter when working is possible is not the total amount of energy. That's the heat at constant pressure, which we talked about in an earlier video. And that is this quantity called enthalpy change. It's abbreviated with delta H. So that means that the first law of thermodynamics could be rewritten as delta E is equal to delta H minus P delta V, which, if we rearrange this equation, allows us to define what enthalpy change is. Enthalpy change is the change in total energy plus P times delta V. If we think about this in absolute terms, which is not super useful, but if we want to just get a complete definition for enthalpy, enthalpy is energy plus pressure times volume. Enthalpy is what we call a non-sensible state function. It's a state function because it does not depend on pathway, but it's non-sensible because there's no way you can directly sense that it's happening. Because constant pressure calorimetry is the easiest to do and often the most reliable, delta H is often the energy quantity that we're going to be most interested in. Common nickname for enthalpy change is heat. So if you see delta H, which is enthalpy change, that could be replaced with heat, and that's probably where the symbol H comes from for enthalpy. A practical example of heat at constant volume and heat at constant pressure occurring is in internal combustion engine. So the cycle that we can graph on a pressure versus volume graph is called the Otto cycle. And if you know how an engine works, the first step is a valve opens and fresh air comes in. That's what's happening now. And then it compresses with the valves closed, and there's a spark, and then it expands, and then it pushes out the exhaust gases, and then the cycle repeats. As this is happening, we can plot out what's happening with increases and decreases in pressure and volume. So now let's freeze this and take a look at the Otto cycle. As the gas is compressed with the valve closed, the flywheel applies pressure to the piston, and that increases the pressure and decreases the volume. Not much energy is exchanged through heating during that process, but a lot of energy is exchanged through working. Then at 2, the spark occurs, the valves are closed, and in a very rapid time frame, the gasoline mixture that's inside of the engine combusts and increases the temperature dramatically. If the temperature goes up and the volume is constant, pretty much constant, that means the pressure is going to rise. So with that addition of energy through heating at constant volume, we get a dramatic increase in pressure. That causes the gas to expand from 3 to 4, and as it does that, it does work on the flywheel. It does work on the surroundings. So that's a loss of energy through working. There's a little bit of loss of energy through heating as well, and that amount would be the enthalpy change that's taking place. And then at the very bottom, the exhaust valve opens, and there's a sudden drop in pressure as the exhaust gases can start escaping out of that valve, and that's a big loss of energy at constant volume. And then the next thing that happens from 1 to 0 and then 0 back to 1 is the valves just stay open. The exhaust valve stays open for the gray part, and the volume is decreased without the pressure increasing, and that pushes the exhaust gas out. And then the exhaust valve closes and the intake valve opens, and that's the blue arrow going back from 0 to 1, and that's increasing the volume but with no change in pressure as the combustion gases enter back into the chamber. If you don't understand how internal combustion engine works, that might have not been so helpful, but if you do have a general knowledge of how IC engines work, that might help give some sense of what working and heating energy exchanges are like in a real life cycle. This is just an ideal, the Otto cycle. In real life, this is what that looks like, and you can kind of see the shape there, but it's not perfect. For a real engine, it's much less about individual distinct steps, but they kind of blend into each other. Now let's talk about enthalpy and different kinds of changes. One type of change is an exothermic change. This is when the enthalpy change is a negative number. In this case, the enthalpy at constant pressure, the heat, is absorbed by the surroundings. So these reactions will feel warm if you're holding them or if you're near them, because energy is going from the system out to the surroundings where you are. And it's also true that the products are going to store less energy than the reactants in an exothermic change. The other type of change is called an endothermic change. And the word parts exo and endo mean out and in, respectively. And therm is a word that's kind of means heat. So exothermic means heat out, and endothermic means heat in. In an endothermic change, just the opposite is true for all of these factors. The enthalpy change is a positive number. That means the system is absorbing the energy. So if you could hold one of these reactions in your hand, it would feel cold because it's taking energy from the surroundings, which is you. And in this case, when the reaction is done, the products that are left store more energy than the reactants that you started with. To keep track of this, we use something called a thermochemical equation. In a thermochemical equation, we show the changes that happen in the particles. That's regular, ordinary chemistry. And then we also tack on what's going on with enthalpy. So here's an example of a thermochemical equation. When water is formed, 2 moles of hydrogen react with a mole of oxygen to form 2 moles of H2O. And the enthalpy change for this reaction is negative 576.6 kilojoules. So that means this is exothermic. That means there's more energy stored in the reactants, the H2 and O2, than there is in the H2O. This is an extensive quantity, this enthalpy change, because it's extensive to how many moles are in the equation. You have to make 2 moles of water for this quantity of energy to be released. So if we cut all the coefficients in half so that we were producing only 1 mole of water, we would also have to cut the enthalpy in half. So the enthalpy change would drop from 576.6 down to negative 285.8, which is half the amount. Another thing that's important about thermochemical equations is that phases matter. For making a mole of liquid water, the enthalpy change is negative 285.8 kilojoules. But if we made gaseous water, we wouldn't be releasing quite as much energy because gaseous water has more energy stored in it than liquid water does. And so that quantity would drop down to 241.8. So you have to pay attention to phase that your substances are in thermochemistry. And another thing is, if we reverse the reaction, that also reverses the energy flow. So when we're making a mole of water, we release 285.8 kilojoules. But if we were to decompose a mole of water into hydrogen and oxygen, that would require an input of 285.8 kilojoules. Enthalpy changes have been investigated for lots and lots of different reactions, and the values have been tabulated for people to use. How they do this is by reporting them all at a standard kind of agreed on set of conditions called standard conditions. So an enthalpy change is considered a standard enthalpy change, and it will have this little degree sign to indicate that it's standard when these conditions are met. One is the temperature is 25 degrees C, or 298.15 kelvins in absolute scale. The pressure is an atmosphere. This is a little bit of a lie. The pressure is actually 1 bar, but a bar is 0.987 atmospheres, and the approximation is close enough because delta H doesn't change that much with pressure. And if there are any solutions involved, then their concentrations are 1 molar. And then these values are often made intensive instead of extensive by always reporting them on a kilojoules per mole basis. One example of a standard heat that could be reported is standard heat of combustion. The little C stands for combustion. So standard heat of combustion, for example, if you combust C4H10, which is butane, this is the balanced chemical equation on the left, and then on the right, we show how much energy change is occurring as that combustion happens. So this is negative 880 kilojoules per mole. It's an exothermic reaction, which is very typical for combustion reactions. That's why we do them, to get the energy out. So here's a question that we could answer using this quantity. How much energy is released if 30 grams of butane is burned? So we could start out with our 30 grams of C4H10. And we know that our enthalpy change, or our standard heat, is given in per mole quantity, so we'll have to convert this to moles using the molar mass of butane, which is 58.124 grams per mole. And then 880 kilojoules are released for every mole. And so when we do this calculation, moles are going to drop out, so are grams. And this is per mole of C4H10. So this will give us just kilojoules. So 450 kilojoules were released when that 30 grams burned. Then we could tack on another question here and ask, what's the temperature of 200 grams of water if this energy was used to heat it up from 10 degrees C? So previously we learned that energy change is equal to specific heat times mass times temperature change. So if we wanted to know how much the temperature changed, we could solve this equation and get Q divided by C times mass, which in this case is 450,000 joules over 4.184 joules per gram per degree C times 2,000 grams. And this would give us a delta T of 53.8 degrees C. Since it started at 10 degrees C, that means it would go up to 63.8 degrees. There are energy exchanges that happen during phase changes, not only chemical reactions. And in general, we can take a look at how much energy is added, if energy is being added, versus temperature. And this is a curve that we would get if we took a substance that was in a solid state and started to add energy to it. First, the temperature would increase until we got to the point where it started to melt. That process would happen at a constant temperature. For water, that's 0 degrees Celsius. Everything has its own melting point. Then, once it was all melted, it would be in the liquid state and the temperature could go up again. Then it would reach another flat spot as it began to boil. So for water, that would be at 100 degrees C. And then the process of vaporization would occur. And then after it's all vaporized, then the gas could start to increase in temperature. Now, if you were taking energy away, this graph would just run in the left-hand direction, and instead of vaporizing, you would be condensing at that top flat spot, and instead of melting, you would be freezing at the bottom flat spot. During the places where there is a change in temperature, the amount of energy that's added or removed is given by the specific heat equation. Q is equal to specific heat times mass times delta T. During the phase change sections, the energy that's needed is proportional only to the amount of substance that you have, and usually that's measured in moles. So during that lower flat spot where you're melting, or fusion is occurring, the energy is equal to this quantity called the delta H of fusion times the number of moles. And during the higher flat spot where vaporization has occurred, the energy that's needed is given by delta H of vaporization times the number of moles. So let's do a big example problem here. What mass of propane would have to be burned to boil 175 liters of water that was initially at 25 degrees C? So if we had this water initially at 25 degrees C, we would have to do two things to it to boil it. We would have to heat it up to the boiling point, and then we would have to boil it all. So the amount of energy that would be needed would be equal to specific heat times the mass times the temperature change, then plus the heat of vaporization times the number of moles. So we have 1,750 milliliters of water, and its density is 1 gram per milliliter. So that means we have 1,750 grams of water. So that's the M that we're going to need in the first term of this equation. And then we can change that into moles by taking our 1,750 grams and using the molar mass of water, which is 18.015 grams per mole. And we find out that N, the number of moles, is going to be equal to 97.1 moles. So now let's go stick that in this equation. For water, 4.184 joules per gram per degree C is the specific heat capacity. we have 1,750 grams. And to get to the boiling point, we're going to have to go up by 75 degrees C, because we were at 25 and water boils at 100. Plus the heat of vaporization. It says here that the heat of vaporization of water is 40.65 kilojoules, but let's change that to 40,650 joules per mole so that the units agree. And then we're multiplying by our 97.1 moles. If you do all the arithmetic here, you come out to 4,580,000 joules to three significant figures. Or, to put it back into kilojoules so we have a more reasonable number that works with our heat of combustion, this is 4,580 kilojoules. The question is what mass of propane would have to be burned, so we're going to go 4,580 kilojoules times 2,220.1 kilojoules per mole of propane. And then the molar mass of propane, which is C38H8, is 44.097 grams per mole. So moles cancel, kilojoules cancel, and this will give us grams of propane. The arithmetic works out to 90 grams. So that's making use of the specific heat equation, the enthalpy of vaporization equation, and a heat of combustion to solve a more complex thermochemistry problem.